Mathematics is often spoken of as the language of the universe, a lattice of symbols, equations, and patterns that does not merely describe the world, but anticipates it. The paths of planets, the swing of tides, the glimmer of eclipses, all unfold with a precision written long before human eyes first observed them. With mathematics, the invisible is made visible, atoms predicted before they were seen, black holes calculated decades before telescopes revealed their shadows. It is a script that seems older than stars themselves, but there are places where this script falters, where the numbers refuse to obey their own rhythm. In the equations of Einstein, there are points where gravity grows infinite, where space collapses into nothing, and mathematics becomes nonsense. In the earliest instant of the Big Bang, equations diverge into infinities that no law can contain. At the heart of black holes, mathematics does not describe reality, it breaks. These boundaries are called horizons. The event horizon of a black hole, the cosmic horizon of the expanding universe, the quantum horizon where particles blur into uncertainty. Each horizon is not only a frontier of space and time, but of knowledge itself. Beyond them, mathematics loses its grip, and the universe slips into silence. So the question emerges, when mathematics fails, is it reality that fractures, or is it our understanding that falls short? Is the universe beyond these horizons truly unknowable, or have we yet to invent the language capable of describing it? This is the story of the places where certainty dissolves, the story of the horizon where mathematics breaks. From the beginning, humanity has turned its gaze to the heavens and sought order in the chaos of stars. The ancients carved the night into constellations, not only for myth, but for measurement. Babylonians tracked the movements of planets across clay tablets. Egyptians aligned pyramids with celestial risings. The Chinese recorded comets and eclipses with a rigor that spanned centuries. And among the Greeks, thinkers such as Pythagoras whispered of a universe governed by harmony, a hidden music of numbers guiding the spheres. Mathematics, even then, was not seen as mere tool, but as truth itself, the hidden bones of reality. When Isaac Newton brought forth calculus in the 17th century, the language of numbers blossomed into something vast enough to capture the dance of the cosmos. His equations of motion and law of universal gravitation revealed the planets as clockwork, the heavens themselves an immense geometry unfolding in time. The idea of collapse or infinity did not haunt his mathematics. For Newton, space and time were absolute, a stage upon which matter moved with precision, eternal and unbroken. But with Albert Einstein came a new stage and a warning. In 1915, general relativity revealed spacetime as no longer fixed, but fluid. Energy and mass could bend geometry itself. Stars warped the sky, light curved around suns, and the very shape of the cosmos was written into equations. Gravity was no longer a force acting across emptiness. It was the curvature of existence itself. Yet woven into Einstein's own field equations were cracks. Solutions emerged that defied intuition regions, where the mathematics no longer yielded smooth answers, but infinities. In 1939, Robert Oppenheimer and Hartland Snyder explored what happened when massive stars burned through their fuel. Their calculations showed that under the weight of gravity, no known force could halt collapse. A star could fall inward without limit until its density and curvature grew infinite. The mathematics spoke of singularities. It was an unsettling revelation. Infinity is not a number. It is a failure of description. Infinities in equations are not results. They are signals that the language itself has broken. Still, singularities were, for a time, treated as curiosities, artifacts of idealized assumptions. Perhaps nature would find a way to avoid them. Perhaps reality was more stable than mathematics suggested. But in the 1960s, Roger Penrose proved otherwise. Using purely mathematical reasoning, he demonstrated that singularities were not artifacts, but inevitabilities. If general relativity was correct, then gravitational collapse must end in regions where the curvature of spacetime becomes infinite. Soon after, Stephen Hawking extended the argument to the entire cosmos. If the universe is expanding, then following the equations backward in time leads to a singularity, a point of infinite density, where time and space themselves began. Mathematics had triumphed in predicting black holes and a cosmic origin, yet it carried its own ghost. For in describing the universe, it had revealed the places where it could no longer describe. Even before these horizons of collapse were formalized, other whispers of the vacuum had emerged. In the 1940s, experiments began to reveal the subtle presence of energies hidden in empty space. The Lamb shift in hydrogen spectra, first measured in 1947, showed that quantum fluctuations altered the very orbits of electrons. Hendrik Casimir soon followed with his famous prediction. Two uncharged metal plates placed micrometers apart would be pushed together, not by any material force, but by the restless energy of the vacuum itself. In 1948, this too was confirmed. Mathematics was supposed to be a language of clarity. Instead, it suggested that nothingness was not empty, and that space-time itself could harbor infinities. By the mid-20th century, humanity had assembled a grand framework. Quantum mechanics governed the microscopic, relativity the cosmic. Together, they seemed to form the twin pillars of modern physics, but in their equations lurked irreconcilable fractures. General relativity described gravity as smooth, continuous geometry. Quantum mechanics described particles and fields as discrete, probabilistic, restless, where the two theories overlapped at singularities, horizons. And the first instant of the Big Bang, the mathematics dissolved into paradox, and yet the observational sky only deepened the unease. Edwin Hubble's discovery of galactic redshifts in 1929 had revealed that the universe was expanding. Later, in 1965, Arno Penzias and Robert Wilson accidentally tuned into a faint hiss on their radio antenna, the afterglow of the Big Bang itself. The cosmic microwave background bathed the sky, proof that the cosmos had once been hot, dense, and far smaller than it is today. It was evidence of a singular beginning, written in microwave light. Thus, the paradox crystallized. Mathematics had guided humanity from the geometry of planets to the birth of the cosmos. It had anticipated black holes before any telescope glimpsed their shadows. It had revealed the afterglow of creation. But with each triumph, it had also uncovered boundaries where it could not follow. Singularities, horizons, infinities. At these places, equations did not yield answers. They yielded silence. The story of the horizon where mathematics breaks begins not with defeat, but with triumph. It begins with the moment mathematics proved itself powerful enough to map reality, only to discover that reality contained edges where no mathematics yet written could hold. And so the great question emerged. Were these infinities a flaw of human understanding, or were they telling us something deeper? Did mathematics truly fail, or had it revealed that the universe itself is built on something beyond numbers? ancients had believed in harmony, Newton in clockwork, Einstein in geometry. Now physicists stood at the threshold of something stranger, a horizon where the language of reality itself fractured into paradox. It is at this threshold that the modern mystery begins. In the history of science, moments of shock often arrive not from what equations fail to explain, but from what they demand we accept. For centuries, mathematics had carried the image of certainty, a language where precision and prediction walked hand in hand. But when general relativity and quantum mechanics were carried to their extremes, certainty cracked. Equations produced not clarity, but infinities. And infinities, in the world of physics, are warnings. At the heart of Einstein's field equations lie singularities. In ordinary conditions, relativity describes spacetime with elegance. Planets orbit in ellipses, stars bend light, galaxies swirl in cosmic harmony. But push the mathematics to its limits. Collapse a star more massive than the sun beyond the point where nuclear fire can resist gravity, and relativity yields no stable solution. Instead, it predicts infinite density, infinite curvature, infinite warping of time and space. This was not simply a curiosity, it was a breakdown. Infinity is not a physical answer. It is the signpost that mathematics has reached its horizon. For the cosmos itself, the same fate seemed written. If galaxies are rushing apart today, then in the past they must have been closer. Trace the expansion backward, and every point in the universe converges to a single, infinitely dense state, the Big Bang singularity, at both the largest and smallest. Scales, black holes, and the birth of the cosmos, relativity declared that the universe had origins in mathematical impossibility. The shock was not only in the equations, but in their defiance of intuition. In 1974, Stephen Hawking revealed a result that stunned even the most seasoned physicists. Black holes, long thought to be the ultimate prisons, turned out to be imperfect. At their event horizons, the restless churn of quantum fields could create pairs of particles. One would fall inward, the other escape. To an outside observer, it appeared as though the black hole itself radiated. This was Hawking radiation. Here, the contradictions sharpened. Relativity insisted that nothing could escape a black hole once. It crossed the horizon. Quantum mechanics insisted that energy and information could not simply vanish. Hawking's insight forced both frameworks together at the edge of the horizon, and the result was paradox. The information paradox emerged. If a black hole radiates, does it eventually evaporate? And if so, what becomes of the information that fell within? Quantum theory is built upon the inviolability of information, the idea that the state of a system, however scrambled, is never destroyed. Relativity, on the other hand, seemed to allow information to vanish forever behind an event horizon. The two laws of physics, each triumphantly tested, collided head-on. Even the vacuum became suspect. Quantum mechanics predicts that even at absolute zero, fields retain energy, zero-point fluctuations, tiny tremors in the fabric of emptiness. These fluctuations are not just theoretical curiosities. They can be measured in phenomena such as the Casimir effect and the Lamb shift. When cosmologists calculated the expected vacuum energy density of the universe, the numbers rose to the largest mismatch in science. Theory predicted a value 10,120 times greater than what observations showed. It was not simply wrong, it was catastrophically wrong. If relativity described spacetime with grace, and quantum mechanics described matter with precision, together, they gave predictions of absurdity. In 1998, a deeper shock arrived. Astronomers measuring distant supernova discovered that the expansion of the universe was not slowing, as expected under the pull of gravity, but accelerating. Something unseen, a pressure woven into the vacuum itself, was driving galaxies apart. This was called dark energy. And in its simplest interpretation, it was vacuum energy, the same zero-point fluctuations that quantum theory had inflated to impossible heights. The paradox deepened. How could one and the same vacuum energy be both unimaginably vast in theory and vanishingly small in observation, yet still strong enough to shape the fate of the cosmos? Physics was not simply confronted with mysteries. It was confronted with contradictions. Each major framework, relativity, quantum mechanics, cosmology, was confirmed by experiment and observation to exquisite precision. And yet, at their boundaries, they denied each other. The closer scientists looked at horizons, black holes, the Big Bang, the edge of cosmic acceleration, the more violently mathematics tore itself apart. Even thought experiments collapsed under paradox. If one imagines an astronaut falling into a black hole, relativity insists nothing unusual happens at the horizon itself. The astronaut crosses without event, though doomed to ultimate destruction at the singularity. Yet from the perspective of an outside observer, time dilates infinitely. The astronaut appears frozen, never quite crossing, their information smeared. On the horizon, both descriptions are mathematically correct and mutually irreconcilable. In 2012, this tension escalated with the proposal of the firewall paradox. If quantum mechanics preserves information, then the horizon of a black hole cannot be smooth. Instead, it must seethe with unimaginable energy, a firewall that would incinerate anything attempting to cross. But this conclusion violated relativity's most sacred principle, that horizons should appear smooth to falling observers. Once again, mathematics did not unify, it divided. The scientific shock lay not merely in the strangeness of the predictions, but in the implications. If mathematics fails at horizons, then the greatest achievements of physics are temporary. If infinities appear, they do not describe reality, but reveal the incompleteness of our description. It is unsettling to imagine that at the most fundamental level, the language that carried humanity from pyramids to particle colliders may not be sufficient. Yet this is where physics now stands. Black holes, the Big Bang, cosmic horizons, each a place where equations predict phenomena that observation confirms, yet each also a place where those same equations collapse into paradox. At the horizon, mathematics itself becomes fragile. It predicts its own failure, and in that failure lies the deepest scientific shock, that reality may be built upon laws we have not yet written, truths we have not yet imagined, and mathematics we cannot yet conceive. The universe, it seems, has boundaries not only in space and time, but in knowledge itself. If the scientific shock was the recognition that mathematics itself could collapse into infinities, the response was inevitable: to look closer, to build sharper instruments, to map the shadows of horizons, and to test the places where equations falter. For if mathematics breaks at certain edges, perhaps observation could show the shape of what comes after. The first laboratory of this search was the sky itself. Black holes, once dismissed as curiosities of Einstein's equations, became tangible. Objects in binary systems, astronomers found stars that danced around invisible companions, their light shifting under unseen gravity. In the 1960s, the discovery of X-ray binaries revealed the ferocious accretion of matter spiraling into darkness, heating to millions of degrees before vanishing. Jets of plasma streamed from galactic cores, powered by engines no star could sustain. Everywhere, the signatures of collapse appeared. And then, in April 2019, came the most haunting image yet, the shadow of a black hole. The Event Horizon Telescope, a planet-spanning array of radio observatories, resolved the supermassive black hole in the galaxy M87. What it captured was not the hole itself, but its horizon, the boundary where light becomes prisoner, a ring of fire surrounding an abyss. A vision once confined to mathematics made real, and with it, confirmation that horizons exist not only in theory but in nature. Horizons also stretch back in time. The cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, is the afterglow of the Big Bang, cooled and stretched by 13.8 billion years of expansion. With missions like COBE, WMAP, and Planck, scientists mapped this faint radiation across the sky, revealing tiny fluctuations, 1 part in 100,000. These were not random. They were the fingerprints of quantum fluctuations, amplified and frozen by inflation, stretched across the cosmos as seeds for galaxies. The map of this primordial horizon told a simple but profound truth. The structure of the universe began as whispers in the vacuum, mathematics written in noise, particle. Physics became the next theater of investigation. The standard model of physics, built in the latter half of the 20th century, described the particles and forces of nature with astonishing precision. Yet it, too, contained hints of horizons. The Higgs field, confirmed in 2012 by the Large Hadron Collider, is itself a relic of collapse. When the universe was young and hot, the field had no preference, and particles were massless. But as the cosmos cooled, symmetry broke. The Higgs field fell into a stable state, bestowing mass upon particles and sculpting the matter. No, it was a collapse in mathematics, reflected in reality. But even this discovery brought new unease. Calculations of the Higgs potential suggest that our universe may be only like a ball resting in a shallow valley. The Higgs field could, in principle, tunnel into a deeper vacuum, a collapse that would rewrite physics itself at the speed of light. The discovery that gives particles their mass may also foreshadow their annihilation beyond particle accelerators. Physicists sought the traces of horizons in subtler experiments. The Casimir effect, first measured in 1948, revealed that placing two metal plates close together produces an attractive force, not from any field between them, but from the absence of vacuum fluctuations allowed in the gap. Nothingness itself pressed the plates together. Later, refinements of the measurement confirmed the eerie conclusion: the vacuum is not void, but alive with energy. Hawking's paradox, too, demanded deeper investigation. Could information truly vanish inside a black hole? To test this, theorists turned to thought experiments and the mathematics of entanglement. The holographic principle emerged, the idea that all the information contained within a volume of space can be described by the information encoded on its boundary. In this vision, the universe itself might be like a hologram, three-dimensional reality projected from two-dimensional horizons. Mathematics breaks at singularities, but perhaps the break is avoided by realizing that the interior is an illusion. The true description written on the edge. Loop quantum gravity offered another path. Instead of treating spacetime as smooth and continuous, it imagined it woven from discrete loops, atoms of geometry too small to see. At such scales, singularities dissolve. The Big Bang becomes not a beginning from nothing, but a bounce, where a previous contraction gives way to expansion. In this picture, mathematics does not break, it transforms. String theory extended the attempt to mend infinities. By replacing point particles with tiny vibrating strings, it smoothed the violent divergences of quantum field theory. Singularities became less like infinite points and more like folds in higher dimensions. Horizons, instead of being walls where mathematics ended, became bridges to other formulations. The price was complexity, a landscape of possible universes, each with its own vacuum, its own laws. Yet within this vision lay the promise of a mathematics that does not break, but endlessly adapts. Even experiments on Earth sought analogues of horizons. In ultra-cold laboratories, physicists crafted Bose-Einstein condensates, states of matter where atoms move in quantum unison. By engineering artificial horizons within them, they created conditions where Hawking-like radiation could be detected. Though faint and fragile, these laboratory horizons mirrored the cosmic, suggesting that even the paradoxes of black holes might be tested in miniature. Gravitational waves offered yet another frontier. Predicted by Einstein in 1916, they were first detected in 2015 by LIGO. The signal came from two black holes colliding, horizons merging, spacetime itself ringing. Each detection since has been not only a triumph of observation, but a test of relativity under extreme conditions. Thus far, relativity has held. Yet each new merger, each new echo, carries the possibility of revealing deviations, places where the equations finally break. Supercomputers, too, became tools of investigation. Simulations of the universe's evolution, seeded with quantum fluctuations, produced webs of galaxies and voids matching what telescopes observe. In these simulations, horizons become visible not only as boundaries of knowledge, but as active agents shaping structure. Each refinement of the models forces mathematics to confront reality with greater fidelity, and each comparison shows both triumph and tension. And yet, despite all of these investigations, black hole imaging, cosmic background mapping, particle collisions, analog horizons, gravitational waves, supercomputer universes, the central unease remains. Horizons persist as edges where mathematics falters. Singularities still haunt black holes and the Big Bang. The mismatch between quantum vacuum energy and observed dark energy remains the greatest numerical failure in science. The information paradox continues to divide the very frameworks of physics. The deeper the investigation, the clearer the pattern. Every advance confirms the reality of horizons, yet none dissolves the infinities that arise at them. Each tool sharpens our vision, but what we see is the breaking of the very language we use to see. Thus, the investigation is both triumph and warning. Humanity has mapped horizons more vividly than ever before, but the paradoxes remain unhealed. Mathematics holds until it doesn't. Beyond that, silence, or perhaps the promise of a new mathematics yet to be written. If deeper investigation revealed horizons with sharper clarity, escalation came from what those horizons implied. For they did not stand alone as curiosities of theory, but multiplied, surrounding reality with boundaries, and at each, mathematics strained, bent, and finally threatened to shatter. The most familiar is the black hole event horizon, a surface with no substance, yet absolute in power. Within its boundary, escape is impossible. Not even light, the swiftest messenger, can leave. For general relativity, The horizon is both triumph and doom. Triumph because it emerges naturally from Einstein's equations. Doom because it conceals a singularity where those same equations predict infinite density, a point where mathematics is not simply incomplete, but self-annihilating. Yet horizons are not confined to collapsed stars. The universe itself harbors one. As expansion accelerates, driven by dark energy, galaxies drift beyond reach. A cosmic horizon forms a boundary, not of gravity, but of expansion itself. Beyond it, galaxies continue to exist, but no signal from them will ever reach us. They slide irreversibly into invisibility, as though the universe itself builds a horizon around us. The mathematics of relativity predicts this with precision. But when quantum theory attempts to describe the energy driving it, infinities erupt. The equations swell into contradictions. A vacuum energy density calculated to be 10,120 times larger than what is observed. The largest discrepancy between theory and measurement in the history of science. And there are subtler horizons still. The cosmic microwave background is a horizon of time, the farthest we can see. It is the moment the universe cooled enough for light to travel freely. Nearly 380,000 years after the Big Bang. Beyond it lies opacity, a universe hidden from view. The mathematics of plasma and radiation describe it, but the singularity before remains inaccessible. Here the horizon is not distance, but origin, an edge of knowledge written into the fabric of time. These horizons, multiplied, raise disturbing paradoxes. In 2012, physicists proposed the firewall paradox. If quantum mechanics is correct, then information must be preserved. If relativity is correct, the horizon of a black hole should be smooth, an innocuous crossing for matter falling inward. But the two together demand contradiction. To preserve quantum law, the horizon would burn with unimaginable energy, a firewall incinerating anything that touched it. Either quantum mechanics fails or relativity does. At the horizon, mathematics cannot reconcile its own laws. The holographic principle, born from attempts to solve such paradoxes, offers an unsettling perspective. It suggests that everything within a volume of space, every particle, every star, even consciousness itself, can be described by data written on its boundary. A three-dimensional universe encoded in two dimensions, projected like a hologram. Horizons, then, are not just limits, but the true repositories of information. If this principle is real, what we call singularities may be illusions, artifacts of misapplied mathematics. But the cost of this vision is staggering. The very notion of inside and outside may be illusions to dark energy intensifies the crisis. With it, the universe does not simply expand, it accelerates. Far in the future, distant, galaxies will disappear beyond the cosmic horizon, their light redshifted into silence. Even the cosmic microwave background will fade. Civilizations born trillions of years hence may never know the true scale of the cosmos, their sky reduced to a lonely handful of stars. For them, mathematics itself would tell a full story, suggesting a static universe with no beginning. The truth will have vanished over their horizon. Meanwhile, string theory and loop quantum gravity, though promising, remain untested. Each seeks to remove infinities, to give mathematics continuity at the horizon. Yet neither is complete, and both face profound challenges. The escalation of horizons forces a deeper question. Perhaps it is not physics that fails, but mathematics itself. For every attempt to resolve contradictions produces new ones. Infinities retreat, only to reappear elsewhere. Singularities vanish in one model, but horizons become opaque in another. Cosmology describes expansion, yet quantum theory cannot explain the energy behind it. Black hole physics insists on information loss or preservation, but never both without paradox. Horizons expand, multiply, divide at the root of the escalation. Is this, mathematics, long considered the perfect mirror of reality, may itself be limited, not because the universe is irrational, but because the frameworks humanity has devised are incomplete. Horizons are not simply physical, but conceptual walls, where thought itself must change shape. The unease deepens. If horizons are boundaries of knowledge, then what lies beyond them may never be known. The singularity of the Big Bang, the interior of black holes, the expanse beyond the cosmic horizon, each may be forever inaccessible, not only in practice, but in principle. Mathematics describes up to the edge, then falters, and yet this very failure is the engine of wonder. For horizons are not absence, but presence, reminders that the cosmos is larger than thought, stranger than equation. They are places where human intellect meets its limits, and in doing so, touches the infinite. Thus, the mystery escalates. Horizons are no longer isolated puzzles. They are the architecture of reality itself. At every scale, from black holes to the universe, boundaries emerge where mathematics trembles, where infinities threaten. The deeper we look, the more horizons appear, multiplying like mirrors facing one another, each reflecting a deeper paradox. The question sharpens. Are horizons telling us that mathematics is wrong, or that reality is deeper than mathematics can ever reach? When mathematics begins to fracture at horizons, speculation becomes the scaffolding of understanding. It is here, in the void between what equations can hold and what the universe demands, that bold theories arise. Each offers a fragment of a bridge across the abyss, a possibility that somewhere beyond the failure of numbers, a deeper logic persists. The simplest attempt to explain the horizon's paradox is the cosmological constant, Einstein's long-abandoned idea resurrected by the discovery of dark energy. In this model, the vacuum itself is filled with an energy that is constant in both space and time, stretching the universe outward. It is elegant, unchanging, a fixed property of spacetime, yet it also remains mysterious. Why should the value of this constant be so small, balanced precisely to allow stars and galaxies to form? Why not immense, crushing matter into oblivion or zero, leaving the universe static? In this apparent fine-tuning, mathematics offers prediction, but no explanation. Others imagine dark energy not as a constant, but as a living field, a force evolving with time. This theory, known as quintessence, portrays cosmic acceleration as dynamic, waxing or waning across the ages. If true, the fate of the universe is not fixed but fluid. Expansion might one day slow, cease, or even reverse into collapse. Here, mathematics does not break, but bends equations, stretched to describe an energy that itself shifts shape across epochs. Yet speculation ventures further still. Supersymmetry, a proposed extension of particle physics, suggests that for every known particle there exists a hidden partner, unseen but fundamental. If true, the vacuum energy of these twin particles could cancel, resolving the catastrophic mismatch between quantum theory and observation. Supersymmetry would make the horizon smooth once more, taming infinities. But no such particles have been found, and the silence of accelerators, like the Large Hadron Collider, weighs heavily. Mathematics whispers of symmetry, but nature does not yet reply. String theory offers an even stranger possibility. In its framework, particles are not points but tiny vibrating strings, each mode of vibration giving rise to mass, charge, and spin. Spacetime itself may emerge from the symphony of these strings, and singularities may dissolve into extended structures. In higher dimensions, 10 or 11, horizons that appear catastrophic in 4 dimensions become gentle folds of geometry. Mathematics, though vast and baroque, survives by transcending the space we inhabit. Yet string theory, rich with possibility, remains beyond experimental reach. It is a map of landscapes we cannot yet walk. Some seek resolution in loop quantum, gravity, where space-time is not continuous but granular, woven from discrete loops of geometry. In this vision, singularities never form, for collapse halts at a fundamental scale. Black holes may bounce, big bangs may become big bounces, horizons may shift into bridges. The mathematics is rigorous, yet the evidence remains elusive. If true, horizons are not endings, but transitions, doors, not walls. From these attempts rises the holographic principle, perhaps the most radical of all. Inspired by black hole thermodynamics, it suggests that all the information within a region of space can be encoded on its boundary, as though reality itself were projected from its surface. In this picture, horizons are not flaws but fundamental. They are the true seats of reality. What lies within is merely shadow. If correct, the universe we know, stars, galaxies, even consciousness, may be the holographic unfolding of data inscribed on a cosmic horizon. Mathematics breaks in the bulk, but survives on the boundary, and beyond horizons, speculation turns to the multiverse. Inflationary theory, with its brief, violent expansion in the first instant of time, predicts that our observable universe is but one bubble in a vast foam. Each bubble forms when a field collapses, freezing into different values, perhaps birthing different laws of physics. Horizons here are not merely limits of perception, but barriers between entire realities. Mathematics describes our bubble, but cannot cross into another. Beyond the horizon, the very rules of numbers may differ. Other visions are darker still. If our universe inhabits a false vacuum, a metastable state, rather than the true ground of energy, then collapse may await. A bubble of lower vacuum could form anywhere, expanding at the speed of light, rewriting all physics in its path. Horizons in this view are not boundaries of perception, but front lines of annihilation, racing outward unseen. Mathematics predicts the possibility, yet offers no comfort. The horizon may one day arrive, not as mystery, but as silence. Each speculation pushes further into the unknown. Supersymmetry, strings, loops, holography, multiverses, all attempt to heal the fractures at horizons, yet none are proven, and all reveal how fragile our hold on certainty has become. Mathematics is no longer a flawless mirror, but a lantern, casting narrow beams into a darkness filled with shapes half seen, half guessed. Still, the act of speculation itself is profound. For horizons do not merely break equations, they invite new ones. They force the human mind to imagine beyond the comfort of tested laws, to entertain realities where dimensions fold, time loops, and universes multiply. The breaking of mathematics is not an end, but an opening, a call to invent, to expand, to dare. And so the paradox deepens. Where mathematics breaks, imagination begins. But whether any of these theories truly resolve the horizons, whether reality itself is constant, dynamic, holographic, or plural, remains uncertain. Horizons are still there, silent, waiting. The horizon where mathematics breaks has not yet been crossed. It may never be. But in the search for answers, humanity has discovered that even the collapse of certainty can be fertile, that the silence of numbers can give birth to deeper visions. At the horizons where mathematics fractures, theory alone is not enough. Humanity turns to tools, vast, delicate, intricate machines that act as extensions of thought, built to press against the limits of what can be measured. These are the instruments that attempt to capture the invisible, to weigh the unseeable, to draw maps where equations tremble. If mathematics falters at black holes, at the birth of the cosmos, and at the accelerating edge of the universe, then telescopes, colliders, and detectors become the hands that reach into the dark. The first of these tools to confront a true horizon was the Event Horizon Telescope. In 2019, its network of radio dishes across Earth joined together, forming a planet-sized eye that captured the first image of a black hole's shadow. The dark center, rimmed with fire, was not merely a picture, but a proof, the horizon of mathematics made visible. It showed that Einstein's equations still hold at the brink of collapse, yet it also set the stage for testing where they might break. Future upgrades to the EHT aim to sharpen the image, to watch the dance of matter in real time, to see if deviations from relativity emerge. Here, technology presses against the singular, asking if the equations still speak truth wherein threaten to reign. Meanwhile, other tools listen rather than see. Gravitational wave observatories, LIGO, Virgo, and KAGRA, have opened a new window on the cosmos. Their detectors, long arms of laser light stretched with precision, register ripples in spacetime itself, born from black hole collisions. Each detection is a laboratory of horizons. When two black holes merge, mathematics predicts a smooth waveform. Yet in the data, subtle deviations could betray cracks in relativity. Already, LIGO's discoveries confirm Einstein's vision too. Exquisite accuracy. But its sensitivity will grow, and with the coming of LISA, a space-based observatory, humanity will hear gravitational symphonies from supermassive black holes, and perhaps from the earliest moments of the universe. If mathematics breaks, it may be in these ripples, where quantum gravity leaves its trace. Beyond the collapse of stars lies the horizon of the cosmos itself. To study this, astronomers build surveys of impossible scale. The Vera C. Rubin Observatory, with its wide-field mirror, will map billions of galaxies, charting how they cluster and move under the pull of dark matter and the push of dark energy. The Euclid mission, launched by the European Space Agency, and NASA's Nancy Grace Roman Telescope will join this effort, tracing the geometry of the universe with unprecedented clarity. These instruments do not look for beauty alone. They seek the fingerprints of mathematics, breaking deviations from Einstein's equations, hints that space-time bends differently on the largest scales, whispers of a horizon beyond comprehension, and deeper still lies the relic light of creation. The cosmic microwave background, the afterglow of the Big Bang, is a horizon of time itself, the oldest light we can ever see. Satellites like COBE, WMAP, and Planck have mapped it with increasing precision, revealing patterns seeded by quantum fluctuations. But the story is not finished. Upcoming missions, such as LIGHT-by-RD and CMBs-4, will probe its polarization, searching for evidence of inflation, the violent expansion that birthed our universe. If detected, it would show how horizons first emerged, quantum fields collapsing, space-time stretching beyond comprehension. Yet here, too, mathematics falters. Inflation predicts a multiverse, an unending cascade of universes, a reality where no equation can describe the whole. These missions may not solve the paradox, but they will measure its shadow on smaller scales. The tools of particle physics confront horizons not of distance, but of energy. The Large Hadron Collider at CERN smashes protons at near-light speed, recreating conditions of the early universe. In 2012, it confirmed the Higgs boson, proving that an invisible field permeates space, giving mass to particles. Yet the Higgs may also be unstable, balanced atop a false vacuum. By measuring its properties with ever greater precision, physicists ask whether our universe is secure or doomed to collapse into a lower state. In these collisions, mathematics teeters. The Standard Model predicts astonishing accuracy, yet cannot reconcile with gravity nor explain dark energy. The LHC and its successors search for cracks, supersymmetry, extra dimensions, new particles that could reconcile broken mathematics. Other experiments attempt to measure the vacuum itself. The Casimir effect, once a subtle curiosity, now becomes a precision probe. Metal plates brought close together shift under the pressure of quantum fluctuations, the invisible storm of empty space. By refining these measurements, physicists hope to glimpse whether the vacuum behaves as predicted or whether mathematics hides a flaw. Similarly, detectors like Xenon and LUX-Zeppelin search for dark matter, the hidden mass sculpting galaxies. If discovered, it would reshape the equations of physics, altering the horizons of understanding in laboratories cooled near absolute zero. Scientists create Bose-Einstein condensates, quantum states of matter that move as a single wave. Within them, analog horizons can be crafted, imitations of black holes where sound, not light, is trapped. These experiments have even produced faint radiation reminiscent of Hawking's prediction. Though tiny, these tabletop horizons reveal how quantum mechanics and relativity might merge. Here, mathematics is tested not by stars or galaxies, but by atoms at the edge of cold. Supercomputers, too, are instruments, though their lenses are made of numbers. Vast simulations evolve universes from first principles, tracking how matter collapses, how galaxies form, how horizons emerge. They compare models with what telescopes see, searching for mismatches that betray deeper truths. These machines test not nature directly, but the mathematics we impose upon it. When the simulated cosmos diverges from the observed, the failure is not of stars, but of equations. And yet, for all this machinery, telescopes that span continents, detectors that hear space-time itself, colliders that recreate creation, condensate, that mimic horizons, the fundamental questions remain open. Does mathematics truly break at horizons, or does it merely shift into a form we do not yet know? Is infinity a flaw of calculation or a feature of reality? Can the universe be fully described, or will there always be places where equations collapse into silence? The race is urgent, for horizons are not eternal. The sky we see is already vanishing, galaxies sliding beyond reach. The afterglow of the Big Bang fades with time, its faint signal growing colder. Black holes consume matter, but their radiation takes eons to reveal their secrets. Instruments must move faster than the universe's own erasure, catching glimpses before they are gone. Science listens, measures, collides, simulates. It stretches its tools across scales from the quantum to the cosmic, seeking to stitch together a mathematics that does not break. But so far, the horizon remains, a boundary where numbers fracture, where infinities rise, where knowledge becomes speculation. And yet, in this pursuit lies the deepest truth. The breaking of mathematics does not silence inquiry, but ignites it. Horizons do not end the story. They define its next chapter. At the boundaries of knowledge, where equations fracture and infinities rise, humanity is confronted with a truth both humbling and profound. The universe does not yield itself fully to description. Mathematics, the language that once seemed infinite in its reach, trembles at horizons it cannot cross. And yet, this breaking is not failure, it is revelation. For centuries, mathematics has been the lantern in the dark, guiding ships across seas, planets across skies, particles across accelerators. It has been trusted not only as a tool but as a kind of scripture, an abstract language believed to mirror reality itself. Newton's laws predicted the arc of cannon fire and the orbit of the moon with equal precision. Einstein's field equations bent the fabric of spacetime, and in their symbols, black holes and cosmic expansion were foretold before any telescope could see them. The power of mathematics seemed unshakable, eternal, but the singularities at the centers of black holes whispered otherwise. The first instant of the Big Bang echoed the same. Here, infinities emerge, not as poetic exaggerations, but as cold results of calculation. Density rising without bound, curvature twisting beyond measure, probability collapsing into contradiction. At these horizons, mathematics ceases to be a transparent window and becomes instead a mirror, reflecting not the universe, but the limitations of human thought. This realization alters the philosophical weight of science. If mathematics does not describe everything, then reality may not be written in equations alone. Perhaps mathematics is not the universe's language, but humanity's, a tool, powerful yet incomplete, shaped by the limits of cognition. Beyond the horizon may lie structures that no equation in our current lexicon can contain. And yet, there is beauty here. For the breaking of mathematics does not diminish wonder, it amplifies it. If reality resists total capture, then mystery remains eternal. Horizons become not walls, but invitations, thresholds urging the mind to invent, to imagine, to reach again in black holes. The paradox is clearest. They are not only physical objects, but philosophical abysses. If information is destroyed within them, then causality itself is broken, and physics collapses into nonsense. If it is preserved, then our theories must bend, creating holographic universes where surface encodes depth. Each possibility reshapes meaning. In one, the universe is fragile, its rules breakable. In another, reality is stranger than imagination, woven in dimensions our senses cannot see. The Big Bang confronts us with the same riddle. At the horizon of time, equations fail. The singularity is not a point in space, but a point of unknowing, a signal that the language of relativity, magnificent though it is, cannot describe the birth of time itself. Was there a collapse before expansion? Was there another universe, another horizon, beyond our own? If mathematics falters here, it is not because reality ends, but because it begins in ways that remain unreachable. Even the accelerating expansion of the cosmos, driven by dark energy, places a horizon before us. Galaxies slip away, not by choice, but by the fabric of space-time itself. Beyond a certain distance, their light will never arrive. The equations tell us this with certainty, but they cannot tell us why the energy of the vacuum is what it is. Predictions diverge by 120 orders of magnitude. Here, mathematics breaks, not in infinities, but in absurdity. Its answers so vast and wrong that they defy meaning. It is as though the universe has written a code we can see but cannot solve. And so, humanity stands in a paradoxical place. At one level, science has never been more powerful. We can image the shadow of a black hole, hear the ripples of spacetime, recreate conditions of the infant cosmos in particle accelerators. But at the deepest level, we are still confronted with silence. The silence of horizons. The silence of equations that end not with clarity, but with collapse. What does this mean for human existence? Perhaps it teaches that fragility is not failure, but condition. Just as stars collapse to forge new elements, so too must theories collapse to create new knowledge. Where mathematics breaks, new mathematics may one day arise. And where even new mathematics fails, wonder itself remains, the inexhaustible fuel of inquiry. There is also a reflection on the human condition hidden here. Each life, too, has horizons of time, of perception, of memory. Just as no telescope can see beyond the cosmic horizon, no mind can grasp eternity. Each individual sees a fragment of the infinite, and within that fragment, meaning must be made. In this way, the breaking of mathematics is not alien to us, it is kin. It is the cosmos reminding us that incompleteness is not a defect, but the essence of being. Perhaps then, horizons are not to be feared. They are the architecture of mystery, the necessary edge that makes discovery possible. Without horizons, there would be no exploration, no striving, no science. The breaking of mathematics is not the end of truth, but the promise of truths too. Come, and yet, a deeper question lingers. If mathematics can fail, then is reality itself beyond human reach? Is there a level of existence that no theory, no equation, no language can ever capture? If so, then the ultimate horizon is not black holes, nor the Big Bang, nor dark energy. It is thought itself, the frontier where consciousness, finite and fragile, touches the infinite and cannot cross. The closing image is one of stillness. Humanity stands beneath the night sky, looking outward to galaxies already lost beyond reach, inward to equations that collapse at infinities. Between them lies a fragile moment, a species that can write symbols of great beauty, symbols that predict, symbols that fail, symbols that reflect its longing for truth. The horizon remains, but so does awe. Where mathematics breaks, the universe does not diminish. It expands into silence, into mystery, into wonder that outlasts equations. And perhaps that is enough. For in the end, the breaking of mathematics is not a defeat. It is an opening, a reminder that the cosmos is not reducible to symbols on a page, but is vaster, stranger, more profound than thought. At horizons, we do not find failure. We find invitation, the call of the unknown, echoing through darkness, urging us to reach again.